So Wanhee and William gave a number of the great aspects of views, and just to reiterate, research has linked good views with improved worker productivity, psychological benefits, health benefits, including reduced surgery recovery times. However, we know that overglazing buildings has negative effects. Usually, the more glass we have, the more energy use, the more energy that our buildings use. And it's not a minor decision. This project that we did showed that window to wall ratio is often one of the most significant design decisions that we can make in terms of the energy performance of our buildings. And since we know that our modern day energy use is leading to climate change, it's worth mentioning that climate change is expected to cause approximately 250,000 additional deaths per year from malnutrition, malaria, diarrhea, and heat stress. This recent research from Harvard and 3 universities in the UK linked 1 in 5 deaths annually in 2018. They said they were caused by fossil fuel emissions. So that's 8 million deaths annually. So we know that considering energy without occupant health hasn't worked well. Consider architecture post-1970s oil crisis, where at best we ended up with unpleasant workspaces, and at worst, many cases of sick building syndrome. But considering occupant wellness without energy, and thus global health, hasn't worked well either. Consider the first generation of LEED certified buildings. Some of them were arguably overglazed, and they were shown to have worse energy performance than their non-green counterparts. So, when it comes to windows, can we do more with less? That was the crux of our project. I also want to talk for a minute about the role of simulation. So I think a lot about design workflows. I practiced in architecture for a number of years. And I think that the way we often use simulation, which is to give one answer, one at a time, about one design iteration to designers, has value. But I think it's much more valuable to give designers an overview of the trends, especially even before they start designing. And so that's what we wanted to help influence with this project, called Visualizing and Evaluating Views from Existing and Proposed Buildings. And this was research I did with Wenting Lee when she worked on her Master's of Design thesis at Harvard GSD. So the first step was simulating view content. And this is something that is very time-consuming in the architectural design process. If you're designing a new building, you kind of have to guess what it is that you might see out of your window. Or if you want to simulate that, it can take a long time. So we found a tool called Google Earth Studio, which is in its beta version right now. It's not quite available to the public for commercial use. But what it allows you to do is to take advantage of Google's 3D models of cities and their extensive street views and aerial photographs. And you can set a camera and you can capture basically a simulated view. And so here's an example that we did where we took photos and we're comparing our photos on the top to the Google Earth Studio results on the bottom. So oftentimes it gives pretty photorealistic results. And we were saying that you could use this in the design process to show what the view might be out of your window before you've even built that window. And we compared that to the traditional method, which might be building a site model or using a 3D model of a city. And we compared the workflows and showed that using this method would save a significant amount of time, 9 minutes versus 100 minutes, for example. And moreover, using the Google Earth Studio method, you would get a photorealistic view, whereas with the traditional method, it might be more simplified. So the next step would be to simulate view accessibility. So this is where we came in. We developed a custom Grasshopper plugin so that you could link your CAD geometry to 3D, to the Google Earth Studio to simulate what the view would be from your actual building, considering things like your window geometry, your orientation, where you are in a room, etc. And so here we're showing how we will capture a view, and then we'll calculate how do the opaque elements of the architecture block that view. And that's what we're showing here. It doesn't necessarily need to be rectilinear elements. You can have round windows, etc. And the other thing we did was to say, let's calculate the view accessibility from within a room. So we suggested picking 5 spots within that room. So what we're showing here is we have the back of the room, the middle of the room, and the front of the room. And then we also want to show the maximal view, like when you pay extra for your hotel room and they say that you have a view of the ocean, it's only when you stand right next to the window on the far side can you see the ocean, but that still counts. So that's what we're doing here. We're saying what's the maximal view extent, which is an amalgamation of standing at both extremes of the window. And the window can be anywhere in the wall. It doesn't need to be centered. And we're also doing this vertically. So we can take account where is the window in the wall vertically. And you notice here that we've also shown features like sun shelves, sunshades, vertical fins. So these are things that you can incorporate into your access to view as well. So what we're doing here with this geometry is we're turning this into a field of view and the inputs that you would need to put into Google Earth Studio. So here what we're showing then is this is the full 360-degree panoramic view that you could get from a spot in a proposed building. And then what these rectangles are showing is the minimal view range from the back of the room, the maximal view range, et cetera, et cetera. So now that we've done this, we're using our tool to rate view quality using the custom Grasshopper plugin. So in this case, we're using user-defined methods. What we do is we output the whole 360-degree panoramic view that one could get. And what you see on the bottom here is now we've designed 4 windows, and those are outlined in blue. And what we've asked the user to do, the user being someone working in CAD like the architect, the user is outlining things that they would like to see, the desirable views, as well as the things that they would not like to see, the undesirable views, such as your neighbor's HVAC equipment. And then what we're asking the user to do is to add in their own point score. So for example, you might decide to give desirable views 100 points per meter squared of view. Undesirable views might get a negative 100 points per meter squared of view, and everything else might get 50 points per meter squared. So more is generally better. And what the user could do is then play with this, try out a few different views and see if the point system felt right. And you can see here how these different windows would score using this system and given the view that I just showed a minute ago. So the reason we wanted there to be a numeric value for the view quality is because it was important to us to be able to incorporate view into a parametric design workflow. We know that window design is one of the most important architectural decisions we can make in terms of environmental performance. But while we're doing that in practice today, we're ignoring view. And we know that in reality, view is one of the most important aspects of a window to the architectural experience of a space. So in this case, we're saying we could link it to other things that we might simulate in a parametric process, meaning we could try out thousands of different design combinations, different sizes of windows, different orientations, different shading designs, etc. And we decided to make a spider plot output where you could rank things like view preference along with other things like energy savings, glare protection, daylight, etc. And then we also decided to output thumbnails of each iteration that we're designing. You can see design option 1 versus design option 2. And what we can do is also show what would the view look like out of each of these designs, and then a thumbnail of that spider plot to show how the performance varies. Then you can use an existing tool like Design Explorer to show users in an interactive way all of the design options that you've simulated. And you can sort through them and you can see trends. And I think that's the really important part, because human designers are optimizing for hundreds of objectives at the same time. It's not just view and energy and daylight, it's aesthetics and egress and safety. And so the idea of giving designers trends, it lets them know things like, what are the second best options and how much worse are they? So if I'm 10 degrees off of south, what does that do for my energy and daylight? Maybe it's not so bad, but maybe it really improves my view, or vice versa. And so here's a summary of our proposed workflow. So we started with that Google Earth Studio, and then we proposed a tool that's a Grasshopper plugin that allows you to simulate the photorealistic view and to incorporate the view access, and then to also qualitatively rank your view score, quantitatively, I mean. And we also use existing tools like daylight simulation and energy simulation. You could be using other tools like the Solema tools, etc., and then using some sort of visualizer such as Design Explorer to visualize all the design options. So future work, I think there's a lot of work to be done in this area. I think there's huge progress to be made. For example, we'd like to make publicly available our tools along with tutorials. There's never enough time for that after a master's thesis. We'd like to develop with collaboration, develop an industry standard view quality score. So instead of this user-defined method that we made, we think that we could work together with the other researchers to come up with a standardized view quality score. And in particular, my team has experience using machine learning, and we'd like to hook that in with crowdsourcing to do a massive human subject undertaking to help develop an industry standard view quality score. Thank you.